5-part series where we've invited distinguished university professors from outside of the department to see. This was organized by Jeff Cooper and Bill Adams, and they have a line of 5 marvelous speakers on tap. And so today we welcome Stephen Brush. Stephen Brush is a professor of history. He's also a professor in IPST, and he's a very distinguished philosopher and historian of science. He received a bachelor's degree at Harvard, and he has a PhD in physics from Oxford. He has more than 300 articles in print, in addition to a number of very well-known books. His most recent books are A History of Modern Planetary Physics, and this is 3 volumes which appeared in 1996 in the Cambridge University Press. He has a book in 2001, Physics, the Human Adventure, From Copernicus to Einstein and Beyond, which was published by Rutgers University Press. And this year he has a book published by the Imperial College of Science in London entitled The Kinetic Theory of Gases. And these are just the recent books. It's a very distinguished collection of publications. He has won numerous prizes, fellowships, editorialships. I won't go through them, but let me just mention an initial one. As a child, he won the Westinghouse Science Talent Competition. And as a non-child, last 2 years ago, he won the Guggenheim Fellowship. And in between, there are many other awards. In recent years, he has been interested in the fascinating question, why scientists accept or reject theories in the physical, biological, and social sciences. It sounds like a simple question. The obvious reason could be that it's true or not true, but there seems to be other reasons why this happens. I said physics. I say, no. Jim and I have had discussions often about truth in physics. Right. So he has all other serious interests in modern evolutionary controversy and in the participation of women in science. Today, Professor Brush will speak on Is Mathematics the Key to the University? Variations on the theme of Wigner.
Thank you. You left out the fact that he's a good advisor on pensions.
Oh yes! In fact, he's now writing a serial. The first came out in the Outlook a month ago, in which he told you the initial details on pension, and you have to wait till the next to find out the real integral details.
Faculty voice, not Outlook.
Faculty voice, yes.
Okay.
So he writes on many subjects.
Okay. Well, I should say for this audience that when I was at Oxford, I was actually working in the Mathematical Institute, and therefore this was a place where we had a mixture of pure mathematicians and applied mathematicians, and I was actually officially an advisee of Charles Coulson, who did quantum chemistry, who was also the professor of applied mathematics. So I have had many pleasant interactions with mathematicians throughout my career, and I was very happy to talk about this subject. So this is the famous paper of Eugene Wigner, as he liked to be called when he came to America. I've taken off from this very intriguing idea that there's something about mathematics that somehow allows you to find out something about the physical universe, and as he said, in some cases you get more out of this than you put in. How can this be? So I am going to talk about some examples in which I think the effectiveness of mathematics is even more radical and more remarkable than Wigner himself said, because I think that it can, in a sense, instigate scientific revolutions, at least in some cases. But just to make contact with the original theme of Wigner, to translate it into a topic that I am a little more familiar with than what he was talking about, the Vanderwaals Equation, which is, I think, well known to many people who have ever studied physics or physical chemistry, is an example where you start from some physical premises, not very accurate, not very justifiable, about the forces and nature of atoms and molecules. You get a cubic equation out of this, and lo and behold, because it's a cubic equation, you find that it can describe the properties of the system not just as a dilute gas, which is where the original assumptions were perhaps valid, but also it can describe the condensation of a gas to a liquid, and it can describe the very remarkable critical phenomena where above a certain temperature and pressure you can go continuously from liquid to gas, hence the title of Vanderwaals' dissertation on the continuity of the gaseous and liquid states. So that's an example of a contribution, you might say lucky, that it turned out that he had a cubic equation. If he had used a more accurate expression for the intermolecular forces, it might not have come out that nicely. And this was certainly an important event in the history of theoretical physics and theoretical chemistry, which initiated and inspired a whole series of works in the late 19th and 20th centuries on the theory of phase transitions and critical phenomena. However, I'm not going to talk about that. Either you already know of this or you don't, and it would take too much time to discuss it. So what I want to do is to look at just a handful of cases where a new theory, inspired and motivated primarily by mathematical considerations, led to a major change in the physical view of the world without people originally intending to do such a thing. In other words, they first did the mathematics, and it turned out they had to fix up the physics in order to agree with the mathematical theory. The first example I want to talk about is Copernicus, who, as you know, proposed a heliocentric theory to replace the geocentric theory of Ptolemy back in the 16th century. And the question has been worrying historians ever since. Why did he do this? What was his motivation? Well, the most recent theory of his motivation, given the fact that he died just as the book was being published, so he wasn't around for the inquiring reporters to go and ask him how did you get this idea. One of the best recent theories of this is that he looked at a set of numbers, the numbers being the periods of the planets as they go around the Earth or the Sun. And in the geocentric system of Ptolemy, if you express things in terms of months, just to get rid of decimals, in the Ptolemaic system, you see that the outer planets, as they are farther away from us, and Ptolemy thought of Jupiter and Saturn as being farther away, closer to the stars, these other planets being closer to the Earth. The farther you go out, the longer the period, which of course makes perfectly good sense, because if you have these celestial bodies going around the Earth, you say, well, how fast are they going? The most natural assumption would be to start off with, they're all going the same linear speed, and therefore the ones that are farther away are going around in a circular orbit, which is going to be bigger, and therefore it takes them longer to go around. Perfectly natural assumption, and a principle which Copernicus thought should be maintained. However, if you look at the first three numbers, you see they're all the same, and it seemed to be sort of unpleasing, unaesthetic, or whatever to Copernicus to have these three objects, Mercury, Venus, and the Sun, all going around in the same period of time, all going around the Earth in 1 year, whereas it would be more reasonable to have a monotonic sequence of numbers. You have these objects going around in something, whatever they go around, and the farther away they are, the longer it takes, okay? So therefore, he played around with the data and found that if you had the Sun be the center, everything going around the Sun, rather than everything going around the Earth, you could in fact very easily achieve this goal. So simply in order to get a nicer looking set of numbers, he started working on the heliocentric system and found that it had some other advantages at the same time. So that's also one of the reasons that other astronomers were pleased with this theory. Now, why did people accept the Copernican system? Well, we have an interesting summary of this from historian of science, as he was at the time, Thomas Kuhn. His book on the Copernican revolution gives you sort of an overview. And the point is that The word infiltration, I think, is the key word at the end of this quotation. In other words, Copernicus proposed a theory which was based on an obviously false hypothesis. Okay, the obviously false hypothesis was that the Earth moves. And of course, everybody in the 16th century knows that the Earth does not move. After all, the Bible says it does not move. Ptolemy says it does not move. And you don't notice any of the consequences that would obviously ensue if the Earth did move. For example, if you said instead of the stars rotating around the Earth in a period of 24 hours, the Earth being stationary, as was generally believed at the time, from the Ptolemaic system, if you were so foolish as to believe that it was the Earth itself that was rotating around its own axis in 24 hours, well, that would give you a ridiculous consequence, because it was known how big the Earth is. It was pretty well known that the, let's say, the circumference of the Earth at the equator is about 25,000 miles. So if you were standing on the Earth surface at the equator, you would feel a wind of 1,000 miles an hour blowing at you if the Earth were going to go around. And of course, you know, a wind of 150 miles an hour is considered a pretty strong hurricane. And of course, if you dropped an object from a tower during the time it's falling through the air, the Earth would be moving underneath it, so it couldn't land at the top of the tower, as it obviously does. So therefore, what happened was that the astronomers decided to treat this as basically a hypothetical theory, despite Copernicus having said quite clearly that he did think the Earth moved. But basically they tried to say, okay, the Earth doesn't move. However, it happens to be convenient to calculate the positions of the planets, to predict eclipses, things like that, as if the Earth really did move. But of course, everybody knows the Earth doesn't really move. And in fact, it was their ambition to reformulate the theory in such a way that they could get rid of this very odious hypothesis about the Earth actually moving. Well, time went by and they didn't succeed in getting rid of it. They got accustomed to using the Copernican theory, using various tables of numbers that were produced by the Copernicans, so that by the time you get to the 17th century, you were sort of stuck with this theory, which everybody knew was based on a ridiculous premise, but nevertheless, what could you do? And so therefore, it was up to the 17th century people, especially people like Galileo, to say, okay, well, yes, of course the Earth moves, even though it's contrary to the physics of Aristotle, so we better get rid of the physics of Aristotle. And that's exactly what Galileo started to do with his law of inertia, which later becomes Newton's first law, which explains why it is that you in fact do not observe these strange consequences of the hypothetical Earth's motion. Okay? So this is a way in which the infiltration of mathematics, I sometimes describe this as a Trojan horse of mathematics, that the mathematicians give you this beautiful theory, which is very nice, pretty empirically very accurate, which you therefore accept. But you don't realize that when you accept the theory, the Trojan horse is containing something which you didn't want, which is the hypothesis of the Earth's motion. But by the time you find out, it's too late, and you have been conquered by that. So I think it's generally acknowledged that this is how modern physics began, by Galileo trying to explain why it is that the Earth actually does move, and yet you don't see the consequences that you, according to Aristotle, would see. Okay, so that's my first example. Now, I should also say that even at the time of Copernicus, or even before, there were indications that this might be an interesting idea to consider. Back in the 16th century, mathematicians were not just people who proved theorems and did calculations at their desks. Mathematicians also included people who made instruments. And in fact, these were often called mathematical instruments. And they were things which had all kinds of practical uses for various purposes, surveying, navigation, and so forth. Here's an example of a mathematical instrument which was made and shown in a book Gamma Frisius is the character who did this, and this is actually from before the publication of Copernicus's book, in which apparently it was useful to have a model in which the Earth actually rotates. Okay, so here's a terrestrial globe which is rotating, made in 1530. And there's a quotation, which actually comes from a somewhat later period, but from the same person, which, in case you can't read the small print, says, "We can do by geometrical invention what is not permitted in the natural world." Okay? So in other words, the mathematician has the privilege of imagining a world in which the Earth is moving, even though it is illegal from the point of view of Aristotle and the Church to think that that is actually what happens. Okay, let's move along to Isaac Newton, who is generally regarded as having sort of completed the scientific revolution, at least in the physical sciences. Isaac Newton now has to cope with a different set of background ideas, which are generally accepted. No longer Aristotle, it's now Descartes. Descartes, in the middle of the 17th century, has proposed a grand philosophy, a grand theory of the universe. And he has said in particular that the universe is completely filled with matter, little pieces of matter, not actually atoms, but pieces of atoms moving around and so forth. And the one thing which everybody agrees that Descartes has asserted is that the only way that you can have action between pieces of matter in the universe is by direct contact. You are not allowed to postulate long-range forces, because that would be just a reversion to mysticism. People who talked about forces in the universe, those were the bad guys that we want to move beyond when we get into modern science. So the basic principle of modern physics, as understood by people in the middle of the 17th century, and as agreed to by Newton, is that thou shalt not ever postulate a long-range force, because that's not scientific. However, what do you do about gravity? Well, Newton writes to his friend Richard Bentley the whole idea of action at a distance, the idea that something can act on itself at a distance, the idea that the moon could act on the Earth or the sun could act on the Earth through empty space is completely ridiculous and abhorrent and unscientific. Okay? Therefore, no man who has any competent faculty of thinking can ever imagine this. Okay, so Newton absolutely strongly repudiates the idea of any kind of absolute long-range force to explain things like gravity. However, he puts together a magnificent theory of the universe based on the idea that the planets, the Earth, the tides, everything else, move as if there were a long-range gravitational force, which, of course, there isn't. Now, how does he reconcile this great achievement based on the assumption of a long-range gravitational force with his own belief and the belief of the time that this cannot be? Well, here is the way he does it, and you're probably familiar with this quotation that he says, "I have not been able to deduce from the phenomena the reason for gravity." In other words, I can't explain to you where gravity comes from, why it acts, okay? And I do not feign hypotheses. Now, everybody has probably heard the phrase hypotheses non fingo, the Latin expression. Unfortunately, this was mistranslated, at least in the English-speaking world, for several centuries to mean I do not frame hypotheses. And it was a French philosopher, Alexandre Koyré, who pointed out the mistranslation, and that the better translation of fingo is feign, meaning to fake a hypothesis. What does that mean? To fake a hypothesis means to propose something as a hypothesis which you don't really believe in, you don't really have any evidence. Just in order to have some explanation, you just pick old any old hypothesis out of the air. And in fact, I interpret this as a hidden dig at Descartes, because that's what Descartes was always doing, was proposing several hypotheses for the same thing which were inconsistent with each other, just in order to see what would happen. So Newton abhorred that type of approach. So basically he said, let's leave this open, a question for the next generation to answer. Or as he said in the other quotation at the end, where did it go? I leave this to the consideration of my readers. And it was exercise for their students to explain where gravity comes from. Okay, I'm not going to, I give up.
We understand it today?
Sure. But, well, I mean, if you accept Einstein's general theory of relativity as, curvature of space-time, or if you want to talk about gravitons, very, little particles going through space and carrying force. So anyway, the result of this was that it was because of a purely mathematical achievement of figuring out, on the basis of this obviously incorrect hypothesis, how the planets move and how all kinds of other phenomena take place. The mathematics drives this whole thing toward saying, okay, you've got to have something like gravity. You've got to accept the idea that the planets move as if there was a long-range force, even though you know there isn't. Well, of course, the outcome of this is gradually you say, well, I guess there must be such a long-range force. We can't find any suitable explanation otherwise. And so this means that in the 18th century, people have now decided, a generation has to pass before these sort of things get accomplished. People then say, well, gee, this was such a great idea to explain gravity as a long-range force. Maybe we can explain a lot of other things by using forces. And so in the 18th and early 19th centuries, you had, in fact, 4 forces eventually. Okay, since long-range force works so well for gravity, let's use it to explain electricity, magnetism, and heat too. Okay, so and this forms a nice symmetrical arrangement. Of course, gravity is only attractive. Electricity and magnetism can be either attractive or repulsive, and just happen to be also inverse square forces. And what you may not be familiar with, if you haven't studied the history of this, is that heat was also, in the 18th century, widely regarded as, in effect, a repulsive force. And this also goes back to Newton, where Newton was trying to explain gas pressure and showed that you could explain Boyle's law of gas pressure by postulating a repulsive short-range force between neighboring particles. And this was sort of generalized, and in the 18th and early 19th century, heat was widely regarded as some kind of a repulsive force, perhaps involving a fluid caloric, perhaps not. Now, people said, well, that's interesting, isn't it? But why are all these forces there? I mean, particularly electricity and magnetism, how come they aren't somehow related to each other? How come there isn't any action of an electric force on a magnetic pole, or conversely? So they started thinking, well, it seems a little clumsy to have different forces for all these things. Maybe they're all just manifestations of one fundamental force. Okay? So this concept of unification was very compelling in the 19th century. It was somewhat associated with what was called German Romantic nature philosophy, Naturphilosophie, because they thought that you could just think about what ought to be and not worry too much about the experiments or even the math. They weren't mathematicians, but nevertheless they did bandy about this idea of a unity of force, that all the different forces such as these are somehow manifestations of the same basic force. And this, in fact, had some historical consequences, namely Ørsted was taken in by this whole romantic idea, and he said, okay, I am going to show that electricity interacts with magnetism, because it must do so according to this philosophy. And it worked. This was what he said himself was the motivation for his discovery of the interaction between electrical currents and magnetic poles. Furthermore, it was apparently one of the various factors that led to the idea of conservation of energy, which some historians would say that was sort of the beginning of the foundation of physics as a distinct unified subject, unified through energy conservation. So this means that the idea of force was actually taken quite seriously, contrary to Newton. However, not everybody else in the physics community bought this idea. In fact, there were still some people who thought that you ought to be able to explain gravity not as a mysterious long-range force, but as bombardment of particles, maybe lots of little particles flying through the air, hitting things, and you have two objects here. The one here gets bombarded from that side, the one here gets bombarded from that side. They get pushed together. Force is stronger if they're closer together, and so forth. So there were all kinds of attempts to derive the law of gravity from what was called a kinetic theory of gravitational particles flying through space. Lots of problems with that theory, which I won't go into, but it simply shows that this is the old Cartesian idea of explaining forces only by impact, by contact, and abolishing the whole idea of long-range force was still popular, even though it was a minority view. And what came out of this was, in fact, not a good theory of gravity, but a good theory of heat, namely the kinetic theory of gases, which regards heat as something to be explained by impacts of small particles, small molecules moving at high speeds, colliding with each other, and so forth. Okay, so that brings us to the next phase of the story, which is the development of the kinetic theory of gases by a number of people who progressively more mathematical, finally getting to James Clerk Maxwell, who decided that he would take up the subject and really do it properly, formulate a proper mathematical theory. Now, when Maxwell was inaugurated as professor at Aberdeen University in 1856, he gave a lecture, his inaugural lecture, which said, among lots of other interesting things, natural philosophy, meaning physics primarily, is and ought to be mathematics. And therefore, if you're going to do physics, you better study pure mathematics first, so that you will be able to do this properly. And conversely, of course, if you're going to do mathematics, you better study physics, because, as he claims, the greatest advances in mathematics have been due to inquirers into physical laws. Okay, so Maxwell made it very clear where he is coming from. If you're going to do physics at all, you better do it from a very mathematical point of view. Now, what Maxwell is known for in this area, of course, is his velocity distribution law, which he proposes. Now, I have put before you, see if we can see the whole thing. This is, as it was published in 1860, is the complete derivation given by Maxwell of the velocity distribution law. Now, I challenge you to find any physics at all in that derivation. It's supposed to be a derivation of the properties of molecules in a gas. Okay? No mention is made of any properties of any molecules aside from their velocities in this derivation. Okay? It's a purely mathematical derivation which relies on, the function which describes this must be symmetrical, must be bounded at infinity or go to zero at infinity, etc. Okay, this is, I should mention also, not Maxwell's original derivation. He basically copied this from John Herschel, who gave it in a book review in 1850, a review of the books of Belgian statistician Kedeley. And of course, it is nothing but the standard normal distribution in statistics, which had, this is a case where mathematics was actually influenced by social science, because that was Kedeley's interest, statistical distribution of various human and social properties. Okay, so Maxwell is saying, okay, of course, if we're dealing with particles, we're dealing with things which obey the laws of Newtonian mechanics. And of course, it's quite clear that the velocities of particles are determined by their collisions, or let's say given, I mean, there's a famous statement of Laplace a few years before this saying that if you knew all the positions and velocities of all the particles in the universe, then by using Newton's laws, you could calculate exactly what those positions and velocities would be at any later time, or conversely, we could work it backwards. Everything is completely deterministic in Newtonian mechanics, assuming, of course, suitable form for the law of forces. So therefore, this was what everybody accepted in the middle of the 19th century. Maxwell did not say, at this point anyway, the molecules move randomly. Because of course they don't move randomly, they move in a deterministic way, determined by Newton's laws. However, if you are going to deal with 10 to the 23rd molecules, it's a little difficult to calculate deterministically all of their positions and velocities, or if you had that information, to use it to calculate the future velocities. So as a practical matter, let's assume that they move as if they were basically random variables, okay? So apply statistical methods to this, not because you think the molecules really are random, but because they are in fact deterministic, but it's convenient and in fact gives you very good results to assume that they behave as if statistically, okay? So we have again this same sort of as if reasoning. The Copernican theory works as if the Earth moved, but of course it doesn't. Gravity can be used to calculate the positions of the planets as if there were a long-range gravity force, even if, of course, that's impossible, and so forth. So this is, again, in the same tradition that you have something, you have a nice mathematical derivation which works and agrees with experiment, and so somehow a new physical assumption, which contradicts what you started with, sneaks in as a result of the mathematical calculation. And so people, physicists, then therefore get accustomed to using the Maxwell distribution law. Boltzmann elaborates it, includes the effect of forces and so forth. And so by the time you get to the 20th century, all physicists are perfectly happy with the idea that they do calculations as if things were random. And so it's no big leap to when somebody says, well, actually, maybe they are random, okay? So here we have this great philosophical change from determinism to indeterminism, which is basically the path has been greased by these calculations based on the assumptions. So here we have Einstein, which this paper of Einstein is one of the first indications in the development of quantum theory that there is in fact a real randomness at the microscopic atomic level, which Einstein is not happy about. Okay, he says the weakness of the theory is that it leaves the duration and direction of the elementary processes to, quote, chance. Who knows what chance means? But nevertheless, I'm confident that this is reliable, okay? So Einstein is, in a sense, partly responsible for introducing the idea of randomness at the atomic level, even though, of course, everybody has heard the famous quotation of Einstein, God does not play dice. So nevertheless, if he had believed that, why did he introduce randomness in his own theory? Well, so then a few years later, we have Max Born, who is responsible for what becomes known as the statistical interpretation of quantum mechanics, which says that, in fact, in the world of atoms, determinism has to be abandoned. Okay, so there is this process by which the Newtonian determinism is gradually, without anybody quite realizing it, being replaced, being undermined, and eventually replaced explicitly by randomness. So that's, and how does it happen? Because the mathematics works out so well when you assume things are random. Okay, now let's step back a few years. What about quantum theory? Now, one of the interesting debates that has been going on in the history of physics community in the last 25 years or so is about who really discovered the quantum theory. Was it really Max Planck or was it really Einstein? And it turns out this was actually another one of the things that Thomas Kuhn did in his role as a historian, was to say, well, actually, if you read Planck's papers carefully, you can't really find anywhere a justification for the idea that the quantization that he seems to be introducing in 1900 in his papers on blackbody radiation really imply or explicitly propose a physical quantization. Why does he do this? Because he's got to calculate the entropy by Boltzmann's formula. Now, you remember Boltzmann, in his elaboration of Maxwell's theory, showed you how you can calculate, for example, the entropy of a system by counting how many ways you can arrange things. Well, you can't count how many ways you can arrange things unless you use integers. At least at that time, there's probably a much more sophisticated type of combinatorial mathematics now that I don't know about. But anyway, at the time, if you wanted to calculate the entropy, you had to say how many ways can you distribute the energy among the various objects, the various particles, or in this case, the oscillators. So in order to use the apparatus, the mathematical apparatus of Boltzmann, in order to calculate the entropy and then to calculate the energy distribution in blackbody radiation, which was what he was trying to do, Planck went back to Boltzmann, found that Boltzmann had done a number of derivations in which he first started off by saying, well, the energy is actually quantized, and then you do the combinatorial calculation, and then at the end you let the size of the quantum go to 0. And so, in a sense, what Planck was doing was taking this purely mathematical hypothesis, which Boltzmann, of course, did not believe the energy is really quantized, it's just a convenient way of getting the formula, and Planck goes through a similar sort of process and then finds that you get the right answer if you ignore the fact that the energy actually is a continuous variable. Now, I think the key, the tip-off to the fact that Planck was not really proposing a physical quantization in 1900 is in the last sentence. After you've done this process, dividing the total energy by the number of energy elements, or quanta, to be divided over the n resonators, then he says, if this ratio is not an integer, which of course it wouldn't generally be an integer if there was a continuous amount of energy allowed to every resonator, we take for p an integer in the neighborhood. So the assumption of quantization is purely for the purpose of a mathematical approximation. It's not presented as a physical hypothesis in Planck's 1900 paper. And in fact, Planck vigorously resisted the idea that let's say, electromagnetic radiation is quantized in space. The only quantization that he was willing to allow was how much energy can be absorbed or emitted by a material object. But he did not, at least until many years later, accept the idea that light, for example, in space is made up of quanta or particles. So the question of whether Planck or Einstein really discovered physical quantization is answered by Planck himself in his Nobel Prize address, where he recounts the history of the subject, and he said, well, I introduced this constant. It could have been just a fictitious quantity, just mathematical juggling, okay? Or you could assume that it's founded on actual physical ideas, rejecting the principle of continuity. Which was it to be? And he says, experience has decided for the second alternative, but this was not for any credit to me, okay? In other words, basically, he says it wasn't my work that produced the physical quantum theory. It was other people, in particular, starting with Einstein, who translated this from a purely mathematical hypothesis to a physical hypothesis. And so that's how quantum theory got started. Now, then we get to quantum mechanics, and again, if you're not already familiar with quantum mechanics, I'm certainly not going to explain it to you in 2 minutes. But this is an example of one of the most famous equations in the history of science. And the thing to notice about this equation is that it says, let's say the stationary, say, psi wave function for the system, this wave function depends on the coordinates of all the particles in the system. Okay, so you have n particles, you have 3 n position variables. They're all linked together in one equation. Okay, now, of course, that's not unusual, but the fact is that it's in the nature of the way quantum mechanics works that you cannot rigorously separate this equation into equations applying to just one particle at a time or 2 particles at a time. In particular, if you're talking about a system of identical particles like electrons or protons or whatever, then you also have an additional constraint that the wave function must be symmetrical or anti-symmetrical when you interchange the labels of the particles. Okay? So this is what gives rise to what is called Bose-Einstein or Fermi-Dirac statistics. In other words, there's a connection between all the electrons in the universe. Okay? Not just the ones in your own little experiment, but all the electrons in the universe are, in some sense, all part of one giant universal wave function. And you cannot completely separate them. Well, that is something which gives rise to some very interesting consequences, as some of you already know in this audience. Okay, but first of all, let's see what happens when you try to make it relativistic, which is what Paul Dirac did. Now, I should mention that Paul Dirac has a special qualification to be mentioned in this lecture since he married Wigner's sister, and therefore is associated with, in that way, with this whole tradition. Okay, so what does Dirac want to do? He wants to solve the problem of duplexity in quantum mechanics. Now, this is not a word that we use anymore, but what it meant at the time was that the electron seems to have a property which has 2 possible values. And you have to take this into account if you're doing calculations. This was then called the spin of the electron by Gauss-Smith and Uhlenbeck. And Dirac says, that's strange. Why should we have to postulate something like that? There must be some reason for it. Well, the reason is because we haven't yet made the equation of Schrödinger consistent with relativity. So let's do that. So therefore, we've got to linearize the equation. We've got to do various things to come out with an equation in which you now have non-commuting matrices, and you have a wave function which, instead of being just one function of the coordinates, is a 4-component function. Okay, all in order to satisfy a purely mathematical condition expressed by things like Lorentz invariance and linearization of the equation and so forth. Okay. Now, so we have 4 wave functions. What does that mean? Well, we can say 2 of them correspond to an electron with spin up and spin down. The spin can have 2 possible values. However, the other one would correspond to some ridiculous thing like an electron that has positive charge, which nobody has ever seen as far as Dirac knows. So therefore, this unphysical. Now, this is one of the things that physicists do when they start with mathematical equations and they get some result, and then they say, well, this equation has 2 solutions, but one of them is obviously unphysical, so we just throw it away. Okay, so Dirac just was following this approach. We can just throw out the other 2 solutions because, after all, nobody has ever seen such a thing as an electron with positive charge. Well, he tries to fuddle around with this and thinks maybe these other solutions refer to the proton. Well, it doesn't work because we know the proton has a lot bigger mass than the electron. Finally, in 1931, he gives up and says, basically surrenders to the mathematical imperative, which is there must be an electron with a positive electric charge. And he publishes this, and then the next year somebody discovers it, Anderson. Okay, so there is a case where we have now a new world in which there are antiparticles. Every particle has an antiparticle. So not only are there positrons, there are antiprotons, anti-this and that, and so forth. So suddenly we have a completely different outlook on the nature of the universe when you now have all these antiparticles, and you say, where are they? You know, how did they get wiped out, and so forth. So So this is a rather radical change in our ideas, simply by trying to satisfy some mathematical conditions to get a relativistic version of Schrödinger's equation. Well, Dirac wrote a famous article in Scientific American in which he gave you the moral of this story. Why is it that he, Dirac, was successful when other people were not in finding the relativistic wave equation and so forth, finding its consequences? Well, other people did it. In fact, he acknowledges that other physicists tried to find relativistic wave equations, but they didn't agree with experiments, so they didn't bother to publish them. And so Dirac says, you weren't bold enough. Just because it didn't agree with experiment, that's no reason it's wrong. And the moral is, it's more important to have beauty in your equations than it is to have them fit the experiment, right? If you're trying to get a beautiful equation, and you of course have to have a sound insight, like Dirac, then you can be sure you're on the right track. And if if you don't have complete agreement between the results of your theory and the experiment, don't worry, because this may be just due to some minor features that are not properly taken into account, and will get cleared up with further developments of the theory. So in other words, follow the mathematics wherever it may lead you, no matter how ridiculous it may seem. Okay, the other consequence, which I've already hinted at, is now called entanglement, and this goes back to the paper published by Einstein, Podolsky, and Rosen in 1935. Now, it's rather unusual for a paper in Physical Review to start off with a definition of reality. But there it is, okay? They're really concerned. What is real and what is not real, okay? They're not philosophers, but they're making obviously philosophical, metaphysical statements. So again, if you're not already familiar with the EPR problem and so forth, I'm not going to try to explain it in 2 minutes, except to say that Bohr, in his reply, says, you are wrong to assume that just because you have one particle here interacting with another particle here, they interact, they go off to another galaxy, and yet somehow you measure the spin or the momentum of one particle here, and it forces the one over there to have the opposite value, and which seems to contradict everything you know about the universe. Nevertheless, the fact that you have in fact tried to measure the property of this particle by making a measurement on that one means that they are not in fact independent of each other, that they are in some way entangled, and of course if you have followed the more recent development of physics, you know that entanglement is the big thing and now is having all kinds of technological consequences. It is a real effect. It can be determined by experiment. Okay, now I hope I have not left you with the impression that mathematics always leads to successful physical theory. And therefore, because there have been other examples when it didn't work, okay? And let me just show you, let's go back to Plato, okay? Plato, like Pythagoras, thought that you could represent the matter of the universe by the 5 regular solids of geometry. They already knew that there were just 5 possible regular solids. Nice little mathematical fact. So 4 of them are the 4 possible elements, and then got a 5th one left over. Well, that must be the cosmos as a whole, or what is sometimes called the ether. Notice this is a dodecahedron, okay? According to Plato, the cosmos is represented by a dodecahedron. Now, Kepler was very enamored of this whole idea, and he thought he could explain the solar system. He could explain, for example, why there are exactly 6 planets in the solar system. That's because there are just 5 regular solids. And to make a model of the solar system, then you nest spheres and inscribed and circumscribed tetrahedra, polyhedra rather, in such a way you choose the appropriate order, and that gives you an approximation to the sizes of the planetary orbits. So Kepler made use of this. Nobody believes this now, so I would say, you would say that was perhaps a failure of over-enthusiasm for mathematics. Another notorious failure was that of Eddington. Eddington was a very good mathematical, physical astronomer, and he thought that it would be possible to derive all the basic dimensionless constants of the universe from pure thought, from mathematics, in particular things like the so-called fine structure constant, which the alpha, which the measurements in physics found to be approximately 1 over 137. And also things like the ratio of the proton to electron mass. Why is it that number? Okay, so here are all these mysterious dimensionless numbers that occur in atomic physics. Eddington thought you could derive them by mathematical theory. And he first found that the fine structure constant should be 1 over 136, and it was pointed out quite forcibly to him by the experimental physicists that this is far from the truth, that it's 137 point something, and it's not even an integer. Well, Eddington found a reason to add 1, so that he then insisted after that that it must be 1 over 137.000. Exactly 137 is the denominator. And similarly, he had a theory which allowed him to calculate the ratio of the proton mass to the electron mass, which he found out with his appropriate mathematics to come out to 1836 point something, not too far away from the value that was known at the time, with appropriate corrections made by Eddington himself. Well, anyway, this is something which was generally regarded as a ridiculous project by other physicists, and nobody took this seriously. Last month, anybody look at Nature magazine? On the cover of Nature is this interesting question: is this the shape of the universe? Okay, and this is the issue of October 9th, just a month ago, and this is a very interesting paper by a group of Frenchmen and one American who have analyzed the data from the cosmic microwave background, which turns out that you don't have a complete Planck spectrum of radiation. The very long wavelengths are not present. One possible reason might be because the universe is finite, therefore it cannot sustain very long wavelength radiation. And so they have analyzed the data and come up with the idea that the appropriate space for the universe is a periodic Poincare dodecahedral space. Now, do we have any experts on the Poincare dodecahedral space in the audience? Anybody familiar with that? Okay, well anyway, that apparently is going to, at least if this is not just a passing fad, that's going to be the next big subject in mathematics. For people, if you're an expert on the Poincare dodecahedral space, you can immediately hire yourself out as a consultant to the cosmologists if this whole thing holds up. Okay, so it may be Plato was right. Anyway, well, we're going to end up with Einstein, basically. And this is, again, a subject of current interest. Einstein developed, by very elaborate mathematical reasoning, his field equations for general relativity back in around 1916. And then he tried to apply them to the universe and discovered that the universe would collapse under its own gravitational force unless he added a repulsive force known as the cosmological constant. This was before the expanding universe concept was generally developed, and when the expanding universe was accepted, Einstein realized this was no longer necessary, and so he officially retracted the cosmological constant in 1931. And he then told people, including George Gamow, this was my biggest blunder in my life to put this in. It really, I had such beautiful equations, and then I messed it up, made them ugly by putting this extra constant. I wish I had never done that. Okay, well, and of course, as you know, within the last 5 years, when the cosmologists have decided that the universe is not only expanding, but also the expansion is accelerating. Bring back the cosmological constant to explain this. Still not knowing what it means, but nevertheless, you know, you can talk about dark energy. So here is the moral that Einstein drew back in 1933, when he had just gone through this painful process of rejecting his own hypothesis and realizing that if he had just stuck with what the mathematics told him and forgot about, you know, what seemed to be an anomaly in the real world, then he would have been better off. And therefore, he said that the way to do science is to do mathematics, just as Maxwell said, and I hold it true that pure thought can grasp reality as the ancients dreamed. Okay, so Einstein again has come to this conclusion. Now we can replace this transparency with my own outline of how these things work. On the board I have written a reference, very recent reference, which if you're interested in the whole problem of Eddington and the fine structure constant and trying to derive the dimensionless quantities, the very nice article by Helga Krog on the subject and archive for history of exact science is now on the shelf in the library. So I'd recommend that if you're interested in the Eddington story. But in the meantime, I guess I better finish because my hour is up. Thank you.
Thank you very much for a very interesting lecture. Are there any comments, questions?
I want to go back to Newton's inverse square law. I mean, this is something we teach that Newton believed in, and this is one of his great achievements.
Yes.
But you're saying that he really didn't believe it? It was just convenient for the mathematics. It made the mathematics work out, so he accepted it? Is that what you're saying?
The thing he did not believe is that something can act at a distance, that matter can have some intrinsic quality that allows it to reach out through empty space and grab something else and pull it toward. That's mysticism. He accepted the idea that that things behave as if there is an inverse square gravitational force. And he put this in the equations. So he believes it in the sense that, yes, it's there in the equations, and clearly, you know, basically it's a confession of ignorance. He says, I can't understand why there should be gravity. Nevertheless, there clearly is something which produces this effect, which can be mathematically described as an inverse square force. I have not come up with any mechanism for gravity that would satisfy the Cartesians, for example. So we'll just have to leave it as a mysterious thing, but there it is, it works empirically. Yeah.
To follow on that question, Hooke had the inverse square,
Right.
which would influence the sun, would influence the planets.
Right.
And Newton was asked by Halley what would be the orbit,
Right.
and he said an ellipse.
Right.
And Halley was very much impressed, asked him to write it up.
Right.
And in looking at the page proofs, he realized that you had to have action and reaction. Mm-hmm. So Newton's real contribution to gravity was the M1, M2 numerator,
Okay.
that the two objects influence each other, which is distinct from what
Yes.
Hooke
Yes.
had.
Okay. Yeah.
You mentioned several times Thomas Kuhn as a historian of
Right.
science.
Right.
Of course, he's also known as a great philosopher.
Right.
I notice you have Scientific Revolution on this thing we
Yeah.
haven't had a chance
Right.
to read.
Right.
Is there any connection, with his whole theory of paradigm shift and so on, and what you would
Sure.
Yeah.
Sure. Let's. Okay, so you can read that there. Yeah, sure. First of all, the Copernican Revolution book, which I quoted, came before the Structure of Scientific
Yeah, right.
Revolutions, and introduces some of the same lines of thought about what revolutions are, without the Gestalt shift ideas and things like that. So I would say Kuhn was afflicted throughout the rest of his life after he published The Structure of Scientific Revolutions with people arguing with him about this and not believing in such a thing as paradigms and so forth and so on. So he tended to withdraw from that whole field, and it was sort of like You know, Einstein's greatest blunder was the cosmological constant. Kuhn's greatest blunder was the paradigm concept, because once he let it out, he couldn't control it. Everybody
I
wanted to.
think he once said, "I'm not a Kuhnian."
Yeah, right. So basically, he didn't want to spend the rest of his life defending the concept of paradigm, so he never used it again, as far as I know, in any publication. But he did continue to do good history, even though you know, everybody was talking about this in a philosophical context. And I think the work that he did on the history of quantum theory, which came out in 1978, I think is something which people didn't take too seriously at the time, but over the next 20 years, as more historians read the original documents of what Planck actually wrote and so forth, they mostly now come to agree that Kuhn was correct. But I think it took a while for people to realize that. Yeah.
Most of the examples of the as-ifs that you gave, we now kind of accept as being real. But in the opposite direction, assuming quantization of things, all the beautiful continuity and that's required for taking functions and the derivatives and all this lovely stuff is therefore, we act as if everything is continuous,
Right.
because it works, when here's one as if which we no longer accept.
Right. So how do you sleep at night knowing this?
Wait a second. The Schrödinger equation and field theory is assumed to be perfectly differentiable. Okay, and string theory and so on is also assumed to be perfectly differentiable. You can observe, and maybe even Newton could have done, that the inverse square force is the solution of Laplace's equation. And what Laplace's equation says is that if I have, you know, few little pieces of stuff here, then what happens in the middle is influenced by the average. So, I mean, it's the calculus that in some sense has concealed the way in which gravitation propagates. And one can, from a philosophical point of view, I think, question, you know, string theory and so on, because there doesn't seem to be any sort of finiteness of matter. Now, you know, nobody's ever found a way of putting that in, and so currently that's one of those things that drops out. But then there's things like the Planck mass and so on that make one wonder. But currently everything is assumed to be calculus.
Boltzmann didn't believe in calculus, by the way. Boltzmann, every time he derived something by calculus, he then went back and derived it by finite differences, as if he didn't believe that calculus was so his papers are twice as long as
a current issue in this thing might be the interpretation of the Everett interpretation of quantum mechanics, where Everett looked at the mathematics of quantum mechanics, and I think for the purpose of irritating people, said, look, you don't have to add various hypotheses that are standard working hypotheses that says when you make a measurement you ignore the Schrödinger equation and interpret the solution some other way. He says you could perfectly well assume that things just go on according to the Schrödinger equation all the time. But if you do that, then the world bifurcates into a huge tree of infinite number of parallel universes, and we living on some random one of them and so forth. And so people always raise their hands and say, of course, this is physical, something else is happening. But that is unsettled at the present time. No one wants, very few people really want to take it seriously, and yet the mathematics is perfectly. Well, don't know anyone who could say Everett made a mistake in his mathematics.
So you're saying that eventually people may be forced to accept Everett's interpretation because there's no other way to explain it.
Well, it's not clear to me, but it's just that this conundrum which he loved to irritate people. I mean, he's very happy that people got all riled up about it. But it was clear that the mathematics suggested one thing, it was obviously wrong.
Thank you very much.